Hello everyone, I'm Sai Venkatakrishnan, a PhD scholar in the Department of Computer Science and Engineering at IIT Madras. So, this is week 6 live session for the course Blockchain and its Applications, the NPTEL course. So, if you have any doubts or queries in the lectures so far in the blockchain course, uh, feel free to unmute yourself and ask those questions or post the questions in the chat box and we can start off the session. So, do you have any specific questions with respect to the course contents up till now in Bitcoin or Ethereum or in any of the course lectures? No doubts? Vivek, Murugeshan, anyone? Any doubts you have? Hello? Vivek, do you have any doubts in the blockchain course up till now? If you have any doubts, feel free to unmute yourself and ask. Unmute and ask. If the doubt is very simple, also you need not worry. You can just post your doubts in the chat box. We can look into it. So, as everyone understood what a smart contract is on Ethereum, how smart contracts are created. So, as everyone understood how smart contracts are created on Ethereum and how they are invoked. Any answers? Manigandan Surya, any idea on how the smart contracts work? You want to chime in on anything? Chime in, correct, Anandi. Akanksha, anyone? How smart contracts are created on Ethereum? So there's a special address called the contract creation address. So have any one of you heard of this address? The contract creation address. So has anyone heard of this address, the contract creation address? So like when you create any smart contract on the Ethereum platform, you should pay some gas fees has to be paid to the mining node which stores the smart contract, right? So so for paying that gas fees and etc., you so if any contract creation or anything on the Ethereum platform, so everything is in the form of transactions, right? So the normal message which is logged on the blockchain is in the form of a transaction. If you are sending some amount to say from person A to person B, the transaction details are simple, like you specify the sender, you specify the destination address, and you specify the amount. But in a contract creation, what will the values of these how will the transaction be created? Who is the destination? You are not sending the contract to someone. You should just store it on the blockchain, and it should be eternally stored on the blockchain, and it should be executed whenever we invoke that contract. So for that, actually, what they have done is they have used a special address like which is all zeros or something like that, which is a specific value, right? And that is they mention it as contract creation address. So in any transaction, if your destination you set it to a contract creation address, then whatever value you specify in your transaction, the payload value, that will be part of your smart contract code. So that is the smart contract code, and that will be stored on your blockchain platform, right? So that is what is known as the contract creation address, and in this way we create smart contracts on the blockchain platform. So any doubts in this? Vivek, Surya, anyone, any doubts in this? Okay. Is there any topic that you want me to explain to you so that you need some explanation, some better explanation on some topic? Because the session usually how it goes is you ask me doubts and I'll try to answer those. And I don't want it to be a repeat of the video lectures that you have seen in during the week, whatever the professor has taught. I don't want to repeat the same contents. So it would be better if you have any doubts, you can post it. You can unmute and ask or post it in the chat box. If you don't have any doubts, then you are free to leave the session.
सर फर्स्ट ऑफ ऑल मुझे ऑप्शन क्या होता है अभी तक क्लियर समझ में ही नहीं आया है।
Sorry, can you speak in English? Hello?
Sir, first of all, I don't understand blockchain. First,
Okay. You don't understand blockchain. So this is, did you go through the week 1 to week 6 lectures, or at least the first 2 weeks lectures? So let me, yeah, speak on. Hello? Right. So Vivek has asked like what's the blockchain? Yeah, I didn't understand. So let me just give a like very high level idea of blockchain. So for others it would be evident, like trivial, like by at this time week in the course, like right. So let us, so for Vivek. So blockchain, the main use case is, say you have multiple parties, right? So say some company C1, company C2, and company C3, and everyone has to maintain a common, say some logbook or something. Like C1 gives some money to C2, and C2 gives some money to C3, and everything should be transparent and it should be known to everyone. So the common thing is you can have some database and everyone has access to the database, and whenever they send some money to the others, they add it to the database. So say C1 sends some money to C2 means it gets added to the database. But the question is, who is in control of the database, and who maintains it, right? Now if we assume that C2 is the leader among the remaining two nodes, then C2 is given the full control of this database, and it's the owner of this database. So it can do any malicious things like, say C2 has sent, it denotes that C2 has sent 100 rupees to C3 means it can just erase that record and just make it like it sent only 50 rupees, something like that, or it can increase the amount or decrease the amount, like that. So if none of the companies are trusting each other and they don't want a single company to be having full control of this database, then there comes the, you can have a blockchain, like a distributed ledger, where instead of having a centralized ledger or the logbook, you can have multiple copies of the ledger. So each company would be maintaining the ledger separately, and they would be there would be a network among these companies, where any transaction they will send it to all the other companies, and they will add it to the ledger. So this is what is called as the distributed ledger, and in this, the blockchain is one way of maintaining the distributed ledger. So blockchain is nothing but it is a list of blocks, okay, like it's a data structure where the last block, the latest block points to the previous block, and it's changed in such a way that if you have to say change any data in this one block over here, if you want to change some data in this block, then all the other blocks would also have to be changed, right? And this will be cost consuming to the attacker based on how you chain the blocks together, and each block will be having a set of transactions, say some 1,000 transactions or anything. Okay. So this is the overall idea of a blockchain, and every node in the blockchain, like every participating party in the blockchain, would be maintaining their own blockchain, and the whole idea of the protocol among all these nodes is to ensure that the same copy is present in all the nodes. They don't have a different copy. Say if C1 sent 100 rupees to C2, then this transaction should be replicated across all the logbooks that each company is maintaining. It should not be the case that this transaction is only stored in this logbook and not stored in this and this. Right? It should be replicated across all the nodes. So that is where you get the blockchain consensus protocol. So everyone should agree on what the logbook is, and everything is done in a distributed way, such that no one is in control of the logbook. No one has like a full control of the logbook or the distributed ledger. So this is the overall idea of the blockchain. I hope that answers your doubt, Vivek. I suggest you go through week one lectures. The professor would have explained the reason why the blockchain was the concept evolved in the first place, and a nice use case, a real world use case, right? So that's it. So anyone else, any other doubts you have, uh, Vishal or anyone, Akanksha, Manikandan? If you are clear with the concepts taught in this week and the previous weeks, and you if you don't have any doubts, then you're free to leave the session. If you have any doubts, you can unmute or you can post in the chat box.
Okay, sir.
So any doubts like how the session would go is like if you ask me doubts, I'll answer those doubts. Apart from that, I don't have much of extra concepts to touch upon. Like those are all like slightly detailed concepts, so it might be slightly off the syllabus of the course. So like first I'd want to solve your queries. So I'll wait for a couple of minutes. If you have any doubts, post it in the chat box.
Hello, sir.
Yeah. Hello, Akanksha.
Yes, sir. So my question is week 7. I
Okay.
don't understand about this how to install Linux system and hyperledgers
Okay.
because my system is Windows, sir. तो फिर और वो it is work only Linux system. So
Can
how can install this?
you can try to install it using the virtual machine. So have you know this virtual machine thing, right?
Yes, sir. Yeah, yeah. I can understand.
Right. So you can download this virtual box by Oracle. Like it's
Yes, sir. I downloaded it.
yeah. So
But
using that you can install.
yes, sir. But some errors like sudo is not working.
Within the virtual box.
Yes, sir.
No, so within that VM image, if you do the sudo commands, it's not working, is it?
Yeah. So it's working, but sudo command is not working.
This command
Already I'm
sudo.
installed this git bash. Yeah.
No, it should work. Like maybe some problem in how you configured. So you created an account, you installed the Ubuntu or whatever Linux based OS,
Yes, sir. I installed it.
and you created the root password and those things, right, in the setup messages. The
No, sir. It's not root password. Is
no, so like when you install, when you install VirtualBox and you should add a VM image to the VirtualBox. So this will be say
yes, sir.
Ubuntu 18 or something. When you add the
Huh,
image,
yeah.
it will install it properly, as in it will ask you to provide a password and username and all those things. So all those steps, did you set up properly?
Okay, sir.
Once if you do those, no, you should use that password to execute these sudo instructions. If you, I guess what you're logging in using the guest mode, I guess, if I'm not.
Yeah. Okay, sir. I'm again checking.
So if so in VM or thing like in the Ubuntu thing, without installing, there is a mode like guest mode or something, where you can just go and try to without requiring the sudo instruction as in the root permission, those things, you can try to execute some code or something like that. But you should do a proper install to execute these instructions and all those things.
Yeah. Okay. Thank you, sir.
Yeah, okay. Right.
I have a doubt in BFT algorithm, how it is works and what. Can you please explain BFT as well as the PBFT as well?
BFT and PBFT.
Yeah.
Okay, that is next week lectures, right, or this week?
Week 6.
Okay. No, so the main idea of BFT is so there are different types of faults, right? You know that. So one is like crash fault and the other is uh, Byzantine fault. Okay. So crash fault is nothing but, say when your node is, if you have a network of nodes, say N1, N2, N3, and N4, okay, and there is and this is a network of nodes, and say suddenly like N2 crashes due to some error, okay, it's a normal crash only, and it might not be able to send messages, okay. So in that case, this is what is a crash fault, and the protocols such as Paxos and Raft, all these things are crash fault tolerant, okay, and they will have an assumption like the number of faults. So the total number of nodes should be greater than or equal to 2f plus 1 or something like that. So the main idea behind this reasoning is, I guess, 2f plus 1. So the main idea behind this reasoning is, if you the majority of the nodes should always be faultless, they should always be working, and in that case, if you get the odds right, say some node uh, proposes a value like um, 5 or something, all the other nodes should agree on that value or not. And what Paxos or any consensus protocol does is, it will send out this value to all the other nodes, and it will wait for the other nodes to reply with an yes or no. And it assumes that all the nodes are acting properly. The only fault that can occur is they might crash suddenly due to some error in their code logic or something. Okay, and since we have this condition that the total number of nodes are always more than 2f plus 1, where f is the total number of faults that can occur, the faulty nodes, okay. And in that case, if we have to rely on this majority voting, right, and if I just divide this 2f plus 1 by 2, it comes around like f plus 1 nodes is always honest, as in they don't have any fault or they don't crash. So I can safely execute the voting algorithm to find out the majority number of nodes, or whether they accept a value or not. I can rely on the reply that I get. So I just need to wait for f plus 1 replies. But the thing becomes complicated, the protocol will become complicated when we take into assumption a Byzantine fault. A Byzantine fault is nothing but, in the previous case, the only error that can occur for a node to stop is it crashes automatically due to some error. But in a Byzantine node, um, it it is not a case that it just crashes, but it can act erroneously, as in it can be that node itself is acting maliciously. It's a bad player and wants to disturb the network. And what it can do is, it breaks the assumption that a node will act honestly. It will act maliciously, and it will send out different messages. So say n1 is proposing the value 5 and n2 is proposing a value 6, means the node 2 will send out differing nodes. It will tell n1 it supports 5, and it will tell n3 it supports 6. And what happens is, node 1 will assume that n2 only voted for 5 and not 6, whereas node 3 will assume that n2 voted for its value and not n1's value. And this differing views, right, because of this, what happens is, n1 will assume that it got its majority vote, and it will decide 5 is the value that everyone agreed upon, and similar way n3 will also assume that everyone agreed upon 6. But finally, when we look at all the nodes, it will have all the nodes will have differing views, and the basic rule that the majority of nodes should have the same value is broken in this scenario, in this Byzantine fault scenario. So to overcome that, only we come up with the PBFT algorithm, or the Byzantine fault algorithm, or the practical Byzantine fault algorithm, right? So in this case, the assumption is, the total number of nodes in the network, okay, n, should be greater than or equal to 3f plus 1, where f is the number of Byzantine faults that can occur, okay, at any time. Only if number of nodes can be faulty in your network, they can act erroneously, and n is the total number of nodes, right? And how they come up with um, this this comparison, or this condition, like n greater than or equal to 3f plus 1, there is a logical explanation, okay. So this is slightly different from what the professor had explained in the video lecture. So say we follow a partially synchronous model, okay. So when I tell partially synchronous model, there are different types of network models, right? When you have different nodes participating in the blockchain network, they will be sending messages to each other, and they will have assumptions. There are three different types of network models. So one is the asynchronous, and the other is synchronous, okay. And the asynchronous model, you won't know when the other party would receive your message. Say node 1 sends a hello message to node 2, you won't know when node 2 will receive that message. It will take a month, it will take an year or so, right? There is no upper bound, whereas but eventually it will be delivered. But whereas in a synchronous message delivery platform, you will for sure know that it will take 2 seconds to deliver the message, everything is working smoothly, okay. But in a real world scenario, you won't always have a synchronous network model. um, there will be network outages in between, the lines would be cut, the on the other side the node would not be available, it would have crashed or something. So what a realistic model of the network, in a real world model of the network should be, is this partial synchronous model, where there will be a synchronous, it will mostly be a synchronous model only, okay. It will mostly be a synchronous model, but at times in between, at times it will behave as a asynchronous model. Say some network outage occurs or something, during that time alone it will behave asynchronously, as in when you send out messages, it don't know when it will get delivered, but it this time will be bounded, as in everyone knows after 1 hour or so my network will be fixed, and it will switch back to this synchronous network, as in every 2 seconds my message would get delivered. That surety I will be having. So this is what almost all the consensus protocol would be assuming, okay. This real world scenario of partial synchronous. So say for the first 1 hour it will be behaving synchronously. For the next say 40 minutes or so, it will be, there will be a network outage, and it will be behaving asynchronously. And then for the next 1 hour, so I will know this asynchronous period will be for 40 minutes, let's assume like this, okay. So for 40 minutes it will be asynchronously, and again it will be in a synchronous way, okay. So this is what is a partial synchronous model. So there will be outages in between, but I will be sure that it will only be there for some period of time, and the engineers will fix the network and it will behave synchronously. So this is what partial synchronous is all about, and this is the model that is followed in all the consensus protocols. Now how we arrive at this the intuitive reasoning behind um, uh, this condition n greater than or equal to 3f plus 1 is, uh, when we tell f is having, if number of nodes are faulty, right, they can either be Byzantine nodes. So they are all Byzantine nodes. That's the worst case scenario. So they will act maliciously. Okay, they can be so they can send wrong messages. Okay, or they can send they can be silent, and they as if some crash had occurred or something, and so that they won't participate in the voting procedure, or they will wantedly confuse your voting procedure. Okay, and in that case, there are totally n nodes. Okay, totally n nodes are there, and out of these n nodes, I am sure that f number of nodes are faulty. So what I'll do is, uh, uh, say one proposal is there, means say uh, uh, some node p, it is proposing a value, uh, say uh, be a uh, blockchain or something, some value it is proposing, and it wants all the other nodes to agree upon this value. Blockchain means what it will do is, it knows that f nodes out of the n nodes are faulty. So what it will do is, it will send out this message to all the other nodes, all the n nodes, but it will not consider the it will not consider um, it will not wait for all the nodes to reply back. It will just wait for 2f plus, it will just wait for uh, uh, n minus f nodes. So it will send out the request to accept this value blockchain to n nodes, and it won't wait for all the n nodes, because out of that f are faulty. Okay, but it doesn't know which nodes are faulty. It just knows that f nodes are faulty. So when it's waiting for the reply, it won't wait for all the n nodes. Instead, it will just wait for all the n minus f nodes to reply back. Okay, and once it gets the n minus f nodes, right, it will again send out to all the n minus f nodes whether it is okay with the value, whatever like accept its blockchain value, whether it will get accepted or not. And now it will wait for uh, the majority, half of this n minus f nodes. Okay, the reason, so now once it gets this number of replies back, and once half of n minus f nodes are replying to accept the value, then it will be sure that all the nodes have accepted this value. Okay, and how we arrived at this expression over here, half of n minus f, is why doesn't it wait for all the n minus f nodes, and why it's just waiting for the half of n minus f nodes is, we have the partial synchrony model. Okay, so we are following this model only, partial synchronous model, and the intuitive reason is, um, I am sending out messages to n nodes, and I'm waiting for at least n minus f replies. Okay, n minus f nodes. So let me give some concrete numbers instead of n and f. So say n equal to 10, and f is equal to 2, f equal to 3. Okay, 3f plus 1, yeah, that suits. Okay, so f equal to 3, and now out of this, say node 1 sends out messages to all the nodes. Okay, and
The
now,
faulty node cannot be 4, right? Sorry.
sorry,
A faulty node should not be 4, right?
faulty
I
node should not be 4. Yeah. So here f equal to 3, and when n1 sends messages to all the nodes, it okay, I'll write it over here. N2, N3, N4, N5, N6, N7, N8, N9, and N10. So it sends out to all the nodes. So it sends out to all the nodes, and now it should wait for at least n minus f nodes to reply back. That is step 1. Okay, so why n minus f nodes is, I know f are faulty, and I will remove f nodes from my scenario. Okay, so what I can do is I will just wait for 7 nodes to reply back, because if I aimlessly wait for all my 10 nodes to reply back, that might not occur, because I know 3 nodes are faulty, and these 3 nodes can be n6, n8 or n9. It can be any 3 nodes out of these n2 to n10. It can be any 3. Okay, and so instead of waiting for all these n2 to n10 nodes to reply back, I should only wait for 9 minus 3, which is what's that, 6 nodes. Okay, so 6 nodes to reply back I should wait, because if I just wait for all the 9 nodes, they might either send, some 3 nodes are faulty, so they can either send um, what conflicting messages, or they will be silent also. Okay, so in that case, for uh, in order to not waste time and all those things, okay, a logical decision is, let's remove 3 nodes out of the procedure. I need not take any take into consideration any of their replies. Okay, so in that case I will just wait. Once I receive 6 nodes. Okay, so this is wrong, not 7. So n minus f. So I'll just wait for 6 nodes to reply back. Okay, and say n2 to n2, n3, n4, n5, n6, n7. So these nodes replied back. Let's assume properly within that 5-second period. Okay, so these 6 nodes replied back, and the remaining 3 nodes, they are replying late or something happened, and what n1 assumes is, n1 would think is, okay, I need not consider these 3 nodes, because they all replied late, or yeah, they have not replied it back, and they can be Byzantine. Okay, but the issue is, we are having a partial synchronous model. So in a partial synchronous model, what happens is, you won't know, so general thing is, you won't know whether a node is Byzantine or not, but you just know how many nodes are Byzantine. So if n8, n9 and n10 don't reply back, you can you cannot for sure tell those nodes are Byzantine, because that these 3 nodes can be, there might be a network outage, so the network might be cut off. These 3 nodes will be honest only, but the network, due to some network disruptions, the messages that they replied back to n1 did not reach n1 in time. Okay, so due to the network outage, like that temporary asynchronous stage, when we discussed in this partial synchronous model, at times it will behave asynchronously. Okay, so due to this feature, whatever the 3 nodes sent back n8 to n10, it didn't receive within that time period for n1. Okay, so that might be a case, and they may not be Byzantine at all. So in that case, the uh, what happens is, um, the Byzantine nodes might be any one of these n2 to n7 actually. So n1, in that case, like whatever it received back, right, 6 nodes, the reply back from the 6 nodes, n2 to n7, out of these 6, anyone can be Byzantine in that case. So it cannot, out of these 6 nodes, then you have to minus again f nodes. So that is 3, minus f equal to 3. Okay, so 6 minus 3, 3 nodes. So out of these 6 nodes, you should again send out request, and out of that you should get at least 3 votes in favor of your decision, and that decision will be the final decision. Okay, so the it's slightly confusing. Okay, so let me explain it in a different way. So we try to assume this. In step 1, it's N1 sends the messages to all the remaining 9 nodes, okay, and now it gets back some replies. It gets from N2 to N7, it gets some replies, that is 6 replies it gets, okay, and the remaining 3 replies it doesn't get. Now there is you can differentiate between two scenarios. In case 1, if these 3 replies from N8 to N10 you don't get it, and if N8 to N10 is Byzantine, right, then you can happily neglect, okay, you can happily neglect these 3 nodes, and what you can do is um, you can just go ahead and assume that these N2 to N7 are honest, okay, they are honest nodes, and whatever they propose, the majority proposes in this N2 to N7, they are um, that is the um, that is the value that you should accept, yes or no, whether the value is accepted or not, you stick with that decision. But case 2 is, since my network can be asynchronous in between, your N8 to N10 nodes might not be Byzantine, they will be honest actually, but their network got cut off in between, and due to that their messages didn't reach in time. So in that case, between N2 to N7, 3 nodes might be Byzantine, they might be erroneous. And now if you just rely um, on the majority of these 6 replies that you got back, then um, then what happens is, um, out of these 6 there are Byzantine nodes, okay, you don't know which are Byzantine, and if you rely blindly on the so you should rely on the majority only, okay, of these 6 nodes, and based on this you come up at this condition n greater than or equal to 3f plus 1, okay. So how we come up with this is, so in case 1 you understood, right, if these 3 are Byzantine, I'm good, you can just look at the first 6 nodes reply. But if these are not Byzantine, but due to some asynchronous nature of the network their messages got delayed, means you should have a um, um, then you are stuck with the problem that N2 to N7, any of these nodes are Byzantine, and you don't know which one to neglect and which one to um, accept properly, okay. So in that case, out of this N2 to N7, there should be, the majority of the nodes should be honest, and they should not be Byzantine, okay. So this part over here, this part represents uh, n minus f, and this part represents f, okay. uh, from these 3 nodes I don't get messages, so since I'm assuming f equal to 3, okay. So over here, so these 3 nodes n8, n9 and n10, I don't get messages, I'm happy they don't reply back, and they can be Byzantine or not. So in that 2 cases are there. One is if they are Byzantine, good enough, that's the easy case, then I can just rely on n2 to n7's decision, and if the majority tells yes, I'm fine with it. But if n8 to n10 are not Byzantine, means um, what happens is, there should be to rely on the majority voting, out of these remaining n minus f nodes, half of them should be honest, more than half of them should be honest, then only I can safely arrive at a decision that um, arrive at a decision whether to accept a value or not, okay. So this is the equation, half of, more than half of n minus f should be honest, okay. So we have given f should be the number of faulty nodes, and we have a condition that more than half of n minus f should be honest. So when we combine both these things, right, so f should be F should be less than half of n minus f. So this is the equation that we arrive at. How we arrived at is uh, we first fixed on the f nodes are faulty. We didn't get reply from say f nodes means we cannot for sure tell those nodes to be assume those nodes to be Byzantine. So out of the remaining n minus f nodes, I want a majority of them should be honest, and that's what this equation is all about. Out of the remaining n minus f nodes, the number of faulty nodes should be less than half of the n minus f nodes. And when I just reassemble, phrase this equation, if I get this 2 to this side, right? So 2f is less than n minus f and n is less than 3f, okay? And if I just add 1 is, so 3f plus 1 less than or equal. So this is the equation that we arrive at. Okay. Any doubt in how we arrived at this equation? This is a bit like sort of intuitive, and there is a mathematical proof to this. But the whole idea is f nodes don't reply, we remove f nodes and we arrive at n minus f nodes. But since due to the asynchronous nature of the network model, we cannot for sure tell whether the f nodes that we neglected were um, Byzantine or not. It can just be they were honest, but their messages didn't reach in time. So my assumption is n minus f nodes, out of that majority should be honest. So my faulty node should be less than half of n minus f, and when I rearrange, I arrive at this equation. N should be greater than 3f, which is the number of nodes should be at least 3f plus 1. So this is the condition that we arrive at. So any doubts in this?
No, I got it. Thanks for the clarification.
Right.
It's really helpful.
Thank you. So now with this condition only, based on this rule only, they have come up with BFT and PBFT. So uh, the difference between BFT and PBFT is in BFT they assume, if I am correct in the lectures, they assume the BFT to have all the synchronous model and all those things, um, which is not um, mimicking a real world setting where you don't have these assumptions always, right? There will be network outages in between, and you might um, all these things. There won't be a, there will just be an upper bound on the message delivery platform, and the adversary might be powerful enough, and all those things. So in that case, they have this. That's why they came up with this practical Byzantine fault tolerance. So they work in this partially synchronous model. There will be some amount of time during which it will be behaving asynchronously, but the rest of the time it will behave synchronously. So that is what they mean by this partial Byzantine fault tolerant. And in this, the high level idea is they will have two stages of voting. So in Paxos, usually when, the Paxos protocol, it's just one stage of voting, as in um, the proposer will just give some values, and if a majority of acceptors tell like I accept a value, then they just lock in on that value, and it's combined together. It's just like one stage of voting. Whereas in practical Byzantine fault tolerance, instead of just sticking with one stage of voting, you have two stages of voting, and the intuitive reasoning behind that is um, in the same way, right? You have received n minus f votes, and you don't want to have a yes or no decision. You don't want to have a binary decision. Instead, if you have a second stage of voting, right, you can have like three decision outcomes on a specific value, whether it was accepted for sure, or it was rejected for sure, or it can be placed in a sort of like a waiting list or somewhere in between, like you accept it, but if a majority of them prove it to be wrong, then you change your decision, right? And that is why they have two stages of voting. If it's just one stage of voting means, if you whatever the majority comes back or whatever replies comes back, out of that the majority you should stick with it, right? But since this is an asynchronous way and the nodes can behave maliciously and all these factors coming into play, you cannot rely on just one stage of voting to arrive at a reasonable decision. And even if you arrive at it's just like two extremes you should decide on, whether it's like yes or a no, accept or reject. You don't have a sort of uh, uh, a neutral position where like okay, like for now we can stick to this value. Maybe it is like an asynchronous stage where messages are not getting delivered properly, but since I know this asynchronous stage will just be for say 40 minutes or 1 hour, once that is over, we can then start asking others and see whether they have accepted the value or not, right? So this sort of flexibility is not there in just one stage of voting, and that's a reason why they have gone for two stages of voting. And the second thing is in the PBFT algorithm, in the first stage they will wait for 2f plus 1 votes, and in the second stage, when they have to finally accept a value, they will wait for f plus 1 votes. And the reason is, even if nodes are faulty, right, the remaining one node is honest, right? And if this one node, honest node, is telling a yes means they have proved mathematically that other than your faulty nodes, okay, my practical Byzantine fault tolerant protocol is safe. And by safe, what I mean is uh, all the honest nodes, apart from the F nodes, the faulty nodes, all the remaining honest nodes will uniformly either accept a value or reject a value. So if I get to know even one honest node's outcome, then I'm sure that all the other honest nodes would have arrived at the same answer or the same conclusion. Okay, and that's why they have waiting for F plus 1 um, uh, replies in the final stage of voting. So it's similar. So whatever PBFT does right, it's just like similar to the voting procedure only, similar to what taxes does, but it just splits it over to two stages of voting, and the number of replies it should wait till it arrives at a conclusion. It varies based on which stage of voting it isn't. So if it's in the first stage, it should wait till 2f plus 1 nodes, and if it's in the second stage, it waits till f plus 1 nodes. But the key point is the assumption is n should be always greater than 3f plus 1 based on the reasoning that we had previously. So any doubts apart from this, Manikandan?
No, I don't have any.
Sorry?
I don't have any other doubt.
Oh, okay.
It's really.
Okay.
Sir, very good evening, sir. Myself, J. Muriasan.
Yeah.
I have one doubt, sir. The smart test network, how to work, sir? There's so many doubt is there. The installation, everything. So if you clearly give the idea about the test network, Fabric one, Hyperledger Fabric.
I have not installed in my system. Like whatever they have explained in the video, you should follow that step by step. It should work out. because the videos are also pretty recent, only 2020 I guess. So if it should work out if you follow step by step the um,
all the
whatever they
video
have.
lecture. Okay, sir. Okay, thank you, sir.
Yeah. Okay. So anyone else, any other doubts in Bitcoin or Ethereum or if you have any doubts, you can unmute yourself and speak up, or you can post it in the chat box.
Hello, sir. Hello, sir.
Welcome, sir.
Sir, what is the real-time use in Hyperledger, sir?
Real-time use case. It can be
Yes, sir.
anything. It can be anything. So the supply chain management and all those things. Um, you have say the supply chain management, right? Like the shipping containers. So that is taken care of, say, one company called um, Maersk, and then you will have the port authority, right? The supply chain is a very good use case of Hyperledger based enterprise solutions, right? You don't want to have it like um, everyone, all the it need not be open to everyone, like to all the population in the world need not participate in this blockchain, but only the entities who are interested in this supply chain management who are participating are, are required to participate, right? So in that case, supply chain management is like an apt example for Hyperledger Fabric and all these things. So if you look at who are all the participants, means the one who delivers the containers, the shipping companies, that is one. The second is the port authority who handles the shipping containers. The third is whoever the end customers who receive the companies who send out the packages or the goods on these containers. So all these companies or entities would be participating in the Hyperledger Fabric network, and that's a good use case, supply chain management. And since it's on the blockchain, right? And also the main use case of blockchain is you don't trust any one single entity, but how you manage how you manage the logbook. So in a supply chain management, a logbook would say, or a transaction would look in a way like say uh, the good reached some destination, say Chennai port at some time, like at 10:30 or something like that, right? And whoever signed this message, who was the inspecting authority, and at what time it was unloaded, and all these details, right? Like real-time tracking. It's a bit complex in supply chain management because your ship would be traveling across multiple continents, countries. If you want to have a transparent way of maintaining the containers and wherever it's going and whether the goods were delivered on time or not, if you have it in a centralized solution, then one single company would be responsible for all the information that has to be uploaded to the network and all those things, and it basically gives that specific company control over the information, and they can act maliciously, or it becomes like a bottleneck, right? And it is not scalable, okay? And whereas if you apply blockchain to this supply chain management, what happens is every city port authority or every port authority will be having their own copy of the blockchain, and once they do an update like goods reach Chennai, this specific container from this specific ship reached a port and was unloaded at the dock or something. If they add it to the blockchain, it will be replicated across all the other nodes in the network, and it will be real time also, and everyone can be um, having the same copy, and they will be it will be like a real time tracking, right? And this is sort of um, like if it's centralized, you don't you're not sure who will be taking care of the storage fees for this much of data to be stored, right? And who will be in charge of the code and all those things. But in a blockchain, everyone comes together to fix upon the code that has to be followed, the rules that has to be followed, and everyone uh, communicate smoothly in a distributed fashion, and everyone are equal stakeholders, right? And in that case, supply chain management is like sort of a good use case for blockchain technology.
Thank you so much, sir.
Okay. So anyone else, any other doubts?
Good evening, sir.
Yeah, hello Sundar.
Yes, sir. Sir, can you explain me how to connect Git and Web3 and how it works?
How to connect JIT and Web3?
Yeah.
No, like any practical like commands related question, I'm not sure because I've not installed those in my system. So the best
Okay,
thing is
but
like to follow that video like
can you explain the code how it's executed and how it works with Git?
this one only, right? You are mentioning JIT.
Yeah.
So maybe I can explain how a smart contract is created and all those things. That theoretical details. Will that be okay? So in the video lectures, you would have seen a smart contract code, something like it will have some keyword contract, uh, and it will be having um, say a function name add or something. It will get two numbers, uint 8, say n1, and uint say a1, uint 8 a2, and then what you do is you will add these numbers a1 plus a2, and that's it. Some computation. I guess this is the example of the smart contract that they showed in the video lecture. Okay, so with this smart contract, the first step in smart contract is you should first of all get this code, and you should compile it down using the Solidity compiler. Okay. So the Solidity compiler will emit a .sol file, I guess. Okay, so this is what is the bytecode, and this is the format. This SOL format, whatever bytecode this compiler emits, this is what would be present on all the nodes in your blockchain network, and it would be so whenever you say you execute a smart contract or something on the network, this specific format only will be it will be loading, and it will be executing on the blockchain network. Okay, so we have created the code, we have compiled it, and we have got a bytecode. Okay, say some arbitrary byte sequence, right? This bytecode we have got, and now we have to store this contract. We have this contract in our local system, but I want to store this contract on the blockchain and make it invocable. Store the contract, and make it invocable. Invocable as in I should make it executable on the blockchain. So for that, what I should do is I should perform a contract create transaction. Okay, so any transaction, if you have gone through the previous lectures, any in a blockchain, there will be multiple blocks, and each block will be having thousands of transactions. Okay, and any way of communicating with your blockchain, or any the smallest unit of information that is stored on a blockchain, everything is in the form of a transaction only. And in Bitcoin, any transaction, it's nothing but say person A, Alice is sending some money to Bob, that's it. Whereas in Ethereum, now you have to store a contract on the blockchain, and you have to form this message in the form of a transaction and send it out to all the other nodes in the network, so that on receiving this transaction, they will store the contract in their own database, or that's the blockchain, and whenever the contract is created, they will invoke it. So so the first step in order to you have um, so you have done this code over here, you have this code, you have compiled it, and now you have to place this code on the blockchain. So for that, you have to do this contract create transaction, and a transaction, there are multiple fields. Okay, so you will have your from address, the to address, and there is a value, payload, and gas fees. Okay, so the from address is like whoever your specific Ethereum address, like the public key address, right? That will be filled over here. And a to address here, I am not sending any money to someone, some ethers or bitcoins to any other entity. Instead, I'm actually creating a contract. Okay, so there is a specific address which is either all zeros, or it will be like some specific address. Okay, say um, 0xCFE cafe. Okay, the address, this to address is a public key address. Okay, and how they have so this 0x cafe is a special address, special as in uh, there won't be a private key corresponding to this public key address 0x cafe. So when I mentioned there is no private key, means only when you have a private key, you can spend your Ethereum, or you can ethers or bitcoins or anything, right? You can spend the outputs. You can spend any amount that you have. But if there is no private key, it is like whatever amount you are sending, or whatever amount you are sending to that specific account, which public key account, if you don't have a private key associated with that public key account, whatever you are sending is just like throwing it in garbage. It cannot be used by anyone. Okay, so in the same way, your contract, whatever you are sending, it should for eternal be online on the blockchain network. So for that, it should not be used up by anyone. It's not like an amount you are sending, it's a code that should always be there. For that, you send it to the special address, and all the nodes in the network would know what this special address is. There is just one specific special address. Okay, and this special address won't have a corresponding private key, as in there is no one who can own this public key address. And once I set this to address, the value I should set it to some value, say 0 or 3. So we'll come back to value later, and now we will set a payload to this whatever contract we got, right, compiled. um, this compiled a bytecode. This bytecode, we will set it to the payload value. This payload content will be the bytecode. So some payload is there, it's part of the transaction, and that is nothing but your actual contract code. Okay, and the gas value is nothing but every node would be executing the transaction, would be performing some operation, and to since the interpreter, whatever interprets this bytecode, right, and whatever you write in this smart contract over here, this computation, this is Turing complete. And by definition, Turing complete is it will go on endlessly. So if you have an infinite loop, right, for I equal to 1, I less than I greater than 0, I plus plus. So this loop will go on indefinitely. This is an infinite loop. Okay, so what happens is, say if I'm a bad node, if I'm a bad programmer or something, I can just write an infinite loop and as part of the contract, and I can send it to the other nodes. And what the other nodes will do is it will honestly try to execute the contract, and it will just infinitely loop over again and again. And this will lead to all the nodes crashing, and this is sort of like a denial of service attack. Uh, you're misusing the service, and you're staging an attack. Okay, so to avoid this, there is a gas fee where you have to pay some uh, values in ethers or way, okay, which is native to the Ethereum platform. And say if you want to perform two add operations, one store operation, you have to um, pay the node whichever is executing the smart contract code. You have to pay them 3 ethers, something like that. So this is what the gas fee is all about, and this for a contract creation based on the on the size of the contract and based on other aspects, right? A gas fee would be set. Okay, so say the gas fee is set to 4 liters. And now when I send this transaction out onto the blockchain, the miner node, what it will do is it will look at this payload value, the bytecode, and it will add this bytecode to the blockchain. Okay, and this bytecode will be given a address, and this is what is known as a contract address. And this contract address, how it derives is it will take the hash of the whole code over here, the hash of the whole code. And once it has taken a hash, right, that is what will be a contract address. So say if you have a function adding two numbers, you take a hash of that code, means you will get a 256-bit value. That 256-bit value, SHA-256 value is the contract address. And once you send out this transaction, right, your contract would be stored on the blockchain. So you have basically created a contract on the blockchain, and it is stored on all the nodes, it's replicated across all the nodes. And now say if you want to execute some contract or something, right, you have to invoke the contract. And by invoking the contract, what you have to do is, again you have to send out a transaction where your from address is the sender, that's the same, but your to address would be the contract address. So whatever I got over here, right, the contract address, that you should specify in the to address. And the payload is nothing but, say I want to invoke a specific function in the contract address, say the add function or subtract function, means that should be part of your payload, as well as all the parameters I should pass. Okay, and now when I send out this transaction, and also there should be a gas fee, like say it has two add operations or one store operation, the corresponding gas fees I should specify over here. And now when this transaction is given to the submitted to the Ethereum blockchain, the mining node, what it will do is it will look into the blockchain, look into which contract has this contract address, and it will take out this contract, it will execute it, based on whatever the payload. So if it wants a add function to execute, it will execute that add function with the parameters that it had passed via the payload attribute, and then it will whatever the output was, it will store it again in the blockchain. It will maintain the state, and whatever gas fees is specified in the transaction, it will deduct from the sender account, and the miner node will credit it to its account address. Okay, so this is what invoking a contract. And say if you want to delete a contract, right? So once if you submit a contract, it will always remain on the blockchain. But say if you want to make a contract no more active, or it should not be invoked anymore, means there is a delete contract or something where you have to invoke, you have to create a transaction where the payload is, instead of invoking the add function or something, you have to invoke the delete function. Okay, and anyway your contract will always be there on the blockchain. But what why is there a delete function, why should it be there, means here I have specified along with the contract creation there is a field called value. So your smart contract code is actually may actually contain ethers also. It can contain some amount in its own account. Okay, and this you can specify in this values field. So it can either contain 0 ethers, or it can contain say 1000 ethers also. Okay, and once you have deposited 1000 ethers in the control of that specific contract code, means um, it is locked in that contract code, and you cannot retrieve it back without performing this delete operation. And once if you delete it, right, whatever amount you had stored in that smart contract code gets reverted back, and it will get stored into your account itself. And so this is the end, this is the life cycle of a contract, starting from how you create a contract via this contract create transaction. You specify the payload, which is your actual code. You specify some value that has to be deposited into the contract, and then you invoke the contract by emitting out some transactions. And then if you don't want the contract to be active at all, you delete that contract. So delete in the sense, you any value or any amount is there, anything you can safely delete it like that. So when you perform a delete operation, right, um, you usually get back all the amount that you have stored in the contract to the sender's account itself. And also you're helping the blockchain, as in all the other nodes, to not actively store this contract. Okay, not all the nodes in the blockchain will be storing the full um, the blockchain, like say 1 terabyte or something. It won't be storing the full blockchain. It will just be storing the last 1000 blocks also. So if you delete this, right, they need not store this smart contract actively. They can safely delete it in their memory, and maybe for backup purpose they can store it somewhere else. But in their actual memory and working disk or something, they can safely delete it. So for that, the sender for um, helping out to reduce the storage, or like to actively delete the smart contract, or help out the blockchain to reduce the storage constraints, right? They get paid back. The gas fee will be negative, as in the the network would be paying the sender some amount, something like that. So you get like bonus points or something if you help the blockchain in deleting some data and making more space, right? So this is the life cycle of a contract. So any doubts in this?
Sir, as you said that uh, denial of service attack will affect to our chain. How does it work and what does it happen?
No. So whenever I invoke a contract, no, over here, if I say how to, so instead of just an add operation, say it has to find the sorting algorithm. Okay, so I am passing an array. So execute. So here the smart contract is a sort, like a ascending order or descending order sorting algorithm, and I should pass an array of numbers. Okay, now if I don't have a limit on the time computation and storage limit, right, what an attacker can do is, since this smart contract has to be executed on all the nodes in the network, not just a minor node, but all the nodes in the network should execute this smart contract when it receives this transaction. So when it receives this transaction, the smart contract should be executed. So when it executes the sort array, if the attacker provides a never-ending list of arrays, or like something like a malicious input, such that when you execute the sort function, it don't exit at all. It will keep on executing. It don't return back eventually. It don't terminate at all. And what happens is all
Got
the
it, sir.
nodes in the network could be executing indefinitely. And this is sort of like a denial of service. As in, the attacker is denying the service to all the other honest participants who want to execute transactions on the network. It is denying that service.
Yes, sir, got it. So
Okay,
can you explain that Ethereum virtual machine?
okay, 1 second. So when Ethereum virtual machine is nothing but whatever. So I mentioned that every node would be executing the smart contract, right? And what is that the smart contract does? The code. Um, so this is the code. This is your smart contract code adding two numbers or something like that. And when you compile it, you get your the solidity byte code. Okay, and this byte code, it should be in a way understandable to someone, right? Then only you will execute it. So say you have a C code, when you compile it, you get x86 instructions. But here your the nodes in the network, say Ethereum has around like 10,000 nodes, of course more than that, and it can be different nodes. One might be running x86, others might be running like AMD machines or ARM systems or RISC-V, all these different architectures and all these things. Okay, and instead of that, what they do is they have implemented Ethereum. They have taken this virtual, they have taken like a layer of abstraction where the code, whatever that solidity compiler generates, the byte code, it is executed on an EVM. Okay, so this add function or anything, whatever the byte code that you get from the solidity compiler, that is targeting a specific machine called as the Ethereum virtual machine, EVM. And this EVM is nothing but a software code. Okay, it's just like another piece of code. And what it does is, say in the byte code which specific to Ethereum, it will be like add uh, 5 6, and it will be say like mem store 11 and something like that. Okay, some sequence of instructions. Okay, this EVM machine would start from the first instruction in the byte code, and it will execute the instructions in a sequential way, and if there is any if else branch or something, it will execute accordingly, and all the results it will store it in the blockchain. And the EVM is nothing but the machine which executes your bytecode. The bytecode is supposed to execute on a machine. In a real world, it is an x86 or something that your the laptop machine or something you are using. But since it is in a distributed way, and different nodes will have different architectures, right? The underlying processor, it will be different. They don't want to get stuck on that aspect. So they came up with this virtual machine, and this is just like another software code, and your bytecode will be executing with respect to this EVM only. And this EVM is like an interpreter. It will just go through every line of the bytecode, execute it. So similar to how you say, I'm running the C code on my laptop, on my processor, x86 processor. In the same way, I'm telling I'm running the bytecode, this, the smart contract bytecode on my EVM virtual machine. That's the same analogy.
Sir, have you seen that in starting videos, blockchain smart contracts and Ethereum smart contracts you are learning at this moment? So, what is the difference between that earlier on and this one? Is there any kind of difference?
I didn't get it. Earlier, what was you telling?
Earlier there was blockchain smart contract, and now we are learning Ethereum smart contract. Is there
Early,
any difference?
Earlier, blockchain is a smart contract, is it?
Yeah.
No, no. See, blockchain is just a term. Ethereum is one specific blockchain. There are multiple
Yeah.
blockchains like Tezos, Algorand, etc. And
Yeah.
everything has its own pros and cons. How it has this gas fee, how it adds the contract, and how it maintains everything is different. Ethereum is one such blockchain.
What is Ethereum smart contract?
No, so whatever we explained, right? Like Ethereum is a blockchain. Ethereum smart contract is like the smart contract that you store it on the Ethereum specific blockchain, right? If you want, so any smart contract that you do, that you code, it is with respect to some specific blockchain only. It's not like like there's one C code, and like that C code is universally acceptable. Not like that, but for Ethereum, there is a set of rules you should follow to code your smart contract. That is what I guess you mean by Ethereum smart contract.
Okay.
Okay, if that doubt is clear, then anyone else have any other doubts? Uh, Manigandan, Rajesh, Akanksha, Sugi, Ria, any doubts you have?
Oh, no, sir. I'm fine.
Okay. Like if you don't have any doubts, then you're free to leave the session. Like,
Thank you, sir.
okay. Sugi and Akansha, any doubts you have? Sugi? Hello? If you have any doubts, we can discuss. I'll wait for a minute or so, else we can end this session. Okay. Thank you, everyone.